Nimit, it is live now. You can start at 4 o'clock exactly. 30 seconds are there.
Thank you.
Yeah.
Shall I begin with the introduction?
Yeah, you can start the introduction. No issues.
All right. So, welcome everyone from around the globe. Today we have in this INCOIS 25 years celebration lecture series, eminent professor, technologist Dr. Kasturi Devi Kanniah from University Technology, Malaysia. She is a fellow member of Malaysia Academy of Sciences and senior member of the Institute of Electrical and Electronic Engineers, IEEE. She has been actively involved in the research, teaching, and consultancy activities in the field of remote sensing technology. Her main research interest, is to link field data with remote sensing technology and to study large-scale vegetation processes and functioning on land and in urban areas, including their role to achieve low-carbon cities and managing atmospheric pollution. Her passion on mangroves started in 2004. That's about 2 decades for now. And she has conducted various studies to map and monitor mangroves extent and their changes in Malaysia using the satellite remote sensing technology. She has also been involved in conserving mangroves through afforestation and reforestation activities and developing policy instruments for local authorities. She is also associated and chief editor of many eminent journals and member of many eminent scientific societies. If I list, we will take a lot of time, so I won't take much of that time. And without spending much time, I will just request Professor Dr. Kanniah to, take the floor and give us this interesting talk. Thank you very much. Thank you again for being with us. Please.
Yeah, you are most welcome, Dr. Nimit. A very good evening, everyone. I thank Dr. Nimit and also INCOIS for inviting me to deliver a talk in this prestigious science talk series. And today I will talk about the use of remote sensing technology for mangrove conservation, which is an initiative to prevent the loss of mangroves. Conservation efforts also include sustainable resource management to ensure their long-term viability, scientific research, community engagement, and the promotion of responsible practices in harvesting and land use. So the title of my presentation is Saving the Green Lungs of the Coast, Remote Sensing for Mangrove Conservation. So what are mangroves? Mangroves are salt-tolerant evergreen forests, usually found in the intertidal environments at the land-seas interface. They grow at tropical and subtropical latitudes, as you can see here. In areas along sheltered coastlines, shallow water lagoons, estuaries, rivers, and deltas. And mangroves consist of trees with medium height of about 30 to 40 meter in optimal conditions. And mangroves also contain shrubs or dwarf mangroves of 1 to 2 meter. However, the tallest mangrove is found in Gabon, Africa, which is about 63 meter. Mangroves are highly adapted to extreme environmental conditions such as salty water by having leaves that can excrete excessive salt. They also have roots that come out of the ground and grow vertically upwards, as you can see here in this picture, to get oxygen for respiration. Mangroves offsprings, they begin to grow while they are still attached to their parent. So this type of plant reproduction is called vivipary. The little seedlings called propagules. I'm holding here one of them, and this picture shows how the propagules look like. They fall off the tree and they lodge into the soil. This is how they survive, and they spread their colonies. And so this This is a short video showing the location of mangroves along the Strait of Johor in Malaysia. So a very short video, just to give you an idea how mangroves is like. Okay, so the global coverage of mangroves as of 2020 was 147,000 kilometers square, from which about 40% is found in Asia. The statistics are provided here in this table. And in Asia, most of the mangroves are found in Southeast Asia, as you can see here. And the mangroves in Indonesia, they have the most coverage with 20% of the entire mangroves of the world, whereas Malaysia and India, they cover 3.7% and 2.7% of the world's mangroves respectively. And not only does Asia have the most abundant mangroves, but this region also hosts a diverse array of mangrove species. Indonesia, for example, has 47 different species of mangroves, while Malaysia has 40 and India 37. And although the global coverage of mangrove is smaller compared to other terrestrial forests, they provide a range of essential ecosystem functions and services such as carbon sequestration, shoreline protection, and habitat for various flora and fauna species. So this figure here, prepared by WWF and IUCN, nicely show the ecosystem services of mangroves. Mangrove wood is utilized for construction and fuel, and the forests also produce other products like tannins, dyes, pharmaceuticals, starch, and honey. These forest products, along with fish and shrimps, they support the livelihood of about 120 million people living near mangroves. So mangroves are considered nature-based solution to protect the coastline and people living nearby from disasters like tsunamis, and they are highly efficient to absorb carbon dioxide from the atmosphere. Thereby, they help to mitigate global warming and climate change. While aquaculture threatens mangrove, well-planned ecotourism can offer sustainable income, raising awareness and encourage conservation. Due to these benefits, mangroves emerge as critical components for sustainable development when they are integrated into coastal management. Mangrove ecosystems, they make crucial contribution to many sustainable development goals set in the 2030 Agenda for Sustainable Development. The importance of restoring and protecting mangrove is reflected most clearly in SDG 14, which is Life Below Water. This SDG is concerned with the sustainable use of marine resources. Mangrove ecosystems also contribute to SDG 1 and SDG 2 by supporting fisheries and producing various forest products, as I just presented in the previous slide. By providing work and economic opportunities through fisheries and ecotourism, mangrove also contribute to SDG 8, decent work and economic growth. It also contributes to SDG 13, climate action. This is very obvious by mitigating climate change through carbon sequestration, and SDG 15 through sustainable forest management and biodiversity conservation. So despite all these benefits that I explained in the last two slides, mangroves face threats due to conversion for profitable activities. So areas that are hotspot for mangrove change are Southeast Asia, as you can see in this picture, which shows mangrove loss from 96 to 2000. Other areas are America and also Africa, especially West and East Africa. According to the recent report prepared by or compiled by FAO, the conversion of mangrove for the production of agricultural commodities like aquaculture, oil palm, and rice cultivation accounted for about 43% of global mangrove loss, as you can see in this picture. And Southeast Asia, as I said, is the hotspot for human-driven mangrove deforestation. Other causes of mangrove loss or degradation are natural retraction due to climate change. Quite a high percentage happens due to natural retraction. Urban development, wood extraction, natural disasters like coastal erosion, and also extreme weather. So another concern is fragmentation, which results in the loss of ecosystem functions even in areas where mangrove cover is relatively stable. I will talk more about fragmentation later in my presentation. So, mapping the extent of mangrove and detecting their changes over time in terms of their coverage and assessing the health of mangroves and quantifying the carbon sequestration are considered crucial steps in the conservation and management of mangroves. For example, mapping provides a baseline assessment of the current extent and also distribution of mangroves. So this kind of information is essential for us to understand the initial state of mangrove ecosystem and identifying areas that need conservation attention. So the ability to detect changes promptly allows us to for early warning of potential threat to mangrove, such as illegal logging, land reclamation, pollution, or climate change. So, timely intervention can help prevent or to minimize the damage to these ecosystems. Accurate mapping data that we get from accurate mapping can be used to raise awareness among local communities about the importance of mangroves and also involving local communities in monitoring and conservation efforts can foster a sense of ownership and also this will encourage sustainable practices. Okay, now come to remote sensing for conservation. Remote sensing is a crucial tool for conserving mangrove because of mainly due to their ability to monitor large areas effectively. Technologies like satellite imagery, they offer consistent data collection, which can help in detecting changes in mangrove cover, their health, and also distribution over time. This helps us to identify threats over time, as I explained in the previous slide. And also remote sensing assesses biodiversity. They are capable of assessing biodiversity within mangrove and also identifying species and habitat for informed conservation strategies. Integrating remote sensing data with other geospatial technology like GIS can enhance our understanding of factors which influence mangrove ecosystems, supporting the development of comprehensive and effective conservation approaches. So I will provide a bit of introduction to remote sensing before I demonstrate some case studies which we have undertaken here in Malaysia. So multispectral type of remote sensing data or sensors, they utilize visual, near infrared and shortwave infrared electromagnetic radiation for locating and monitoring mangroves. So as you can see in this graph here, so due to their different biophysical and chemical properties like water, cellulose, lignin, protein content, and leaf pigments such as chlorophyll and also keratin, due to this differences in these properties, mangroves absorb and reflect light differently across multiple wavelength or band, as you can see here. So they have a special spectral signature, as you can see in this picture. So mangrove, they have different reflection properties in comparison to other land use or land cover or features on the earth. And one of the most important series of multispectral remote sensing satellite is Landsat program, which has provided long-term multispectral data sets. And there are many studies being conducted using these data sets to map and monitor mangroves, including some global products such as that of Chandragiri 2011, Hamilton and Cassie 2016, Bunting 2018 and 2022. And the latest product from not product latest kind of mangrove product from FAO, they produce in just in 2023. So the increasing advancement of multispectral satellites has also developed finer spatial temporal resolution. Landsat is medium resolution with 30-meter spatial resolution. So other satellites such as Sentinel, Spot, QuickBird, Worldview, Rapid Eye, Iconus, and etc. They have also been used recently to study mangroves, mainly because they have very high spatial resolution ranging from 0.5 to 5 meter. However, one very serious problem with this kind of optical data is cloud coverage. I'm sure everybody knows about it. The different biophysical and chemical properties, as I mentioned in the previous slide, um, uh, they are also not only they are different between mangrove and other features, but also among mangrove different species, they have these properties differently. So this different properties are utilized or used to identify or classify different species, as you can see here. So this is a study conducted in Vietnam, where just using with spectral data, two different types of species, mangrove species, can be identified in this study. And another type of important remote sensing data, which is very, very useful for mangrove studies, is hyperspectral. And this sensor offer valuable information for studying mangrove because they provide large number of continuous spectral bands or narrow spectral bands. They often operate between 380 and 2,500 nanometer with a narrow bandwidth of less than 10 nanometer. So this allows hyperspectral sensors to better distinguish between different types of vegetation, particularly different species of mangrove, and accurately estimate their properties such as biomass and carbon content. Quality optics and efficient light collection systems of this kind of hyperspectral sensors, they contribute to better light gathering capabilities, and this allows the sensor to capture stronger signals from the target and minimize the impact of background noise. So however, these sensors can only produce data for smaller area. So this picture here shows a study conducted in Malaysia. So where multispectral satellite, this is hyperspectral handheld spectrum radiometer was used to identify a total of 19 different species of mangroves in Malaysia. Yeah, another important satellite data is the synthetic aperture radar, and since multispectral and hyperspectral are passive remote sensing system, they have limitations to operate during all weather, and also they subject to cloud contamination. So radar system, on the other hand, adopts active microwave imaging technique, and they utilize microwave wavelength from like about 1 centimeter to 100 centimeter, and they are able to penetrate clouds and also dense mangrove canopy. So therefore, they can provide much more information about mangrove. And the most widely used SAR sensors are like the Sentinel-1, NVSAT, ALOS Pulsar, and RadarSat. So this data with different wavelength, they give additional benefits in mangrove mapping, and especially in the estimation of carbon stock, which I will talk about in a while. So for example, X-band, as you can see here, X-band is shorter with about around 3 centimeter. They cannot or rarely penetrate deep into mangrove canopy, and therefore they cannot penetrate deeper. They can only penetrate the surface layer, and they can provide information about canopy surfaces, whereas longer wavelength like L band, they can penetrate deeper into the trunk up to the soil surface, and also into stems and branches, which is very, very important to study species structure and also to get the carbon stock, for example, of the entire mangrove ecosystem. And another important feature of synthetic aperture radar is their polarimetric characteristics. SAR sensors commonly use horizontal and vertical polarizations. As you can see here, different polarizations can be used to distinguish characteristics of mangrove from other objects. For example, VH and HV are most sensitive to the branches and leaves of mangrove, so therefore they can be effectively used to study carbon stock, for example. And another satellite data, satellite or airborne or terrestrial data that can be used for mangrove is the light detection and ranging, LiDAR. And this is another active remote sensing approach that can provide highly accurate and detailed measurements of vegetation structure, especially the height, which is important indicator for carbon stock in mangrove. Some LiDAR system, they have ability to penetrate through vegetation canopies, and they can also map underlying terrain and allowing for the creation of digital elevation models that can be used to estimate volume of sediment and also carbon. Okay, so there are also spaceborne LiDAR systems such as the GLASS, and which stands for Global Ecosystem Dynamics. The GLASS system. It's not on top of my head now. And also recently, the Global Ecosystem Dynamics Investigation, or JEDI, by the NASA, they have also been used to estimate global mangrove canopy heights, and the retrieved canopy height information is used to estimate the carbon stock of mangrove. Okay, so now I would like to present some of the works that we have done in Malaysia. So in the southern region of Peninsular Malaysia, here, we have 3 of the 7 Ramsar sites, namely Kukup Island. Kukup Island, this is the whole island is covered by mangrove. And also Tanjung Piai. Tanjung Piai is this area here, and this is Pulai River. This is the biggest mangrove in the southern region with about 9,000 hectare. And this region, this region is called Iskandar, Malaysia. This is a fast-growing national special economic region with a total area of 2,200 kilometers square. So a lot of developments are taking place in this region. So we wanted to know if mangroves are affected at all due to these developments, which have been going on actively since 2006. So we classified the region, the land use and land cover of this region using Landsat thematic mapper, enhanced thematic mapper, and OLI, covering 1989, 2000, 2005, 2007, 2009, 13, and 14. So here, this work was published back in 2015. So we use traditional per pixel classification technique called maximum likelihood, which was widely used due to their capability, and also rather easy to use, but yet can provide reliable results. So we wanted to show that with sufficient and representative samples, even not so complicated techniques like maximum likelihood can produce better results. So the overall classification accuracy of these 6 classes classified was quite high, ranging from 88 to 94%. So water bodies and mangroves produced higher user and producer accuracies among all these classes of more than 76%. Rubber, for example, rubber had slightly lower classification accuracy, mainly due to their mixture with forest. And here we report the change in different land use and land cover. In each year, as you can see in this graph, oil palm constitutes the largest land area compared to other land use, land cover. In 89, rubber was the second largest land use, and this was followed by urban, forest and mangrove. This distribution started to change since the beginning of 90s, where the land used for oil palm plantations increased 43% in 2005 and onwards. Urban land use increased steadily from 89 until 2014, as you can see here, with a rate of 1,000, more than 1,000 hectare per year. Land used for rubber plantation decreased drastically, and all this, the increase in oil palm and decrease in rubber was associated with the government policy to increase or to boost the economy of the country. When we focus on the mangrove, we found a 33% reduction occurred between 89 and 2014. This is equal to about 240 hectare per year. And from 2005 to 2014, about 1,500 hectare of mangrove was reported, we found to have lost. And the analysis of satellite imageries also show that over a period of 25 years that we analyzed in this study, Iskandar, Malaysia lost about 6,700 hectares of mangrove. However, over the years, Iskandar, Malaysia also gained about 700 hectares of mangroves. I don't know if you can see it very clearly here. So especially this part of the region, it gained more mangroves, mainly due to initiative taken by Iskandar, Malaysia, and also other authorities to have more mangroves, or to increase the mangrove coverage. Generally, natural green cover forest and mangrove, they suffered losses of as much as 65% for forest and 33% for mangroves. So this is another study. In this study, on the same region, since we are in Johor, so we tend to do more research in this area because we get a good support from Iskandar, Malaysia as well. So we applied here machine learning techniques on retrieving mangrove areas from both Landsat and Sentinel data. So Sentinel started to be available from 2015 onwards. So we also utilized that data. So the main purpose of this study was to analyze mangrove fragmentation and its impact on mangrove health. So changes in the extent of mangrove, here we cover the period 2000 to 2019. So changes in the extent of mangrove cover has resulted in fragmentation that can greatly affect the functions and services of mangrove and their impact to the environment and human. So what is fragmentation? So fragmentation, it refers to the subdivision of a continuous landscape into smaller units, which can be characterized based on their patch size, edge, and shape modification. So the use of support vector machine in this study to classify the Landsat and Sentinel imageries showed great capability by clearly distinguishing mangrove from forest and also water bodies, which often can be misclassified. So from the classification results, the loss of mangrove is noticeable, as I have presented on this slide. Particularly where it has been converted to urban area and oil palm plantations. So we found an expansion of the urban area, especially at the eastern side of here, this area, you can see the red color, where the new township, there was a new township developed in this area, and in the central part of this region here, where here also a new township came up. So these new townships had to be developed to accommodate the ever increasing population in this region. So interesting the conversion of mangrove to aquaculture land use was found at multiple locations, which showed the recent development and expansion of the economically valuable aquaculture activities in this region. So overall, as here, this figure shows a net loss of 21% of mangrove occurred in this region between the period that we analyzed. And this is equal to about 1.1% of annual mangrove loss. And this percentage is actually higher than Malaysia's mean depletion rate of mangrove, which is about 0.4%. This is based on estimation by Hamilton and Casey. They also used satellite data. So the southwestern part of this region, as you can see on the far left here, as also I showed previously, where the Ramsar sites, these regions are, southwestern is this part. Here, this area also faced significant loss. And on the other hand, at the eastern part here, new patches of mangrove were noticed. And the new mangrove areas is blue color. I hope you can see them clearly. And as I said, the reduction is due to township and also for developing housing and other activities. And as I just mentioned before, so during the identification of gain and loss locations, we also identified about 40 sites in this region. The mangroves were used for aquaculture activities. And aquaculture conversion from mangrove forest is very popular, not only in Malaysia, but also in Indonesia, where 40% of mangrove loss in Indonesia in the past decade was found to be converted to aquaculture. So this figure here shows the locations, and most of the aquaculture sites are located at the boundary of mangrove. And at the eastern side of this region, here, more aquaculture sites were found compared to the western side where the Ramsar sites are located. And one of the reasons could be the Ramsar sites are protected from these activities, while on the eastern side where the Johor River flows here, the accessibility to water from this river and the reach of nutrient of the site encourage the conversion of mangrove area to aquaculture use. And this is another study that we published last year. So here, this show a further mangrove loss within a river basin, and it caused a change in the Johor River morphology. From 1990 to 2020, in this region alone, mangrove shrank about 30%, and mainly due to port development and also an expressway construction. So this is Johor River, and we can find mangroves along the river. And in this slide, I just want to highlight how changed river morphology. And this figure show part of the Johor River, two sections, cross section along the river. On the 2020 image, this one, the right side, one of the section marked by the yellow rectangle. Here, mangrove area, which was noticed in the 2010 image, it disappeared by 2015. And possibly due to heavy development and also expressway construction, as I mentioned previously. And these activities caused or damaged mangrove. Additionally, aquaculture activities also here, you can see along this site. And also other land reclamation near the estuary may contribute to river channel migration of about 1 to 2 kilometers in this region over the past 30 years. Okay, so now I want to spend a bit of time on talking about mangrove fragmentation, which I mentioned previously. So based on the fragmentation analysis as listed here, a reduction of the total landscape area of approximately 3,000 hectare was found between 2000 and 2019. This reduction actually can limit the movement zone of animals and discourage flora and fauna succession within or between the fragments. An increased number of patches from 130, you can see here in this table, from 130 in 2000 to 402 in 2019, and decreased mean patch size from 105 to just to 27 hectare, increasingly isolated mangrove patches, and this can lead to a loss of connectivity between patches. For example, in this area, this is the biggest mangrove area that I showed you before, called Sungai Pulai. One large patch in 2000 was fragmented into 60 smaller patches in 2019. And this can prolong the migration of animals to surrounding habitats due to decreased existing habitat size, which can stimulate species extinction. And Malaysia has highest reduction of mangrove mean patch size, ranked at the first place in the nations of the world, and this is reported as reported by Brian Brown in 2020. And the age and shape indices, as you can see here, they reveal that human-induced disturbance is significantly influencing the mangrove 8 to 1.9 show a reduction of shape complexity, which could be due to the transformation of mangrove area, which is irregular shaped into regularly shaped or spaced patches of urban agricultural and aquaculture. So this changes of edge and shape complexity, it can ease human access to the fragmented patches and exploit the remaining mangrove areas in the future. So we found increase in number of patches, total age density, whereas decrease occurred in terms of total area, size, and also shape index. Okay, so this slide also, I just want to take a bit of time to explain about the impact of fragmentation on mangrove health. So here we used leaf area index and gross primary productivity to check the health index of mangrove due to fragmentation. Leaf area index is an important indicator for predicting photosynthesis, respiration, transpiration, and also rainfall interception. While GPP, it refers to the total amount of carbon entering the ecosystem, and it serves as one of the most important parameters in global carbon analysis and ecosystem assessment. But studies looking at this kind of processes are very few. Li and GPP in this study were retrieved from Modi's sensor. These products are available at 1 kilometer spatial resolution and at 8 days interval. So we extracted Li and GPP values from mangrove areas that underwent changes like growth, loss, gain, and fragmentation, and also mangrove areas that did not change between the two time period that we analyzed. So the Li and GPP values from the unchanged, please look at this table. From the unchanged mangrove area increased, actually they increased from 2000 to 2019. This indicates that the mangrove leaf area has grown over time when nobody disturbs, and it enabled higher carbon uptake. Similarly, the Li and GPP from mangrove gain area also increased between the two time period. On the other hand, the mangrove loss area recorded mean Li decrease. The loss of native mangrove trees which have dense leaf to oil palm which have less dense canopy may be the main reason for the reduced Li values. For fragmented mangrove areas, the mean lies show a slight increase while a large change occurred in GPP. This finding is interesting, and you may be asking me why fragmented patches show higher carbon uptake. So out of the 60 fragmented patches that I showed in the previous slide, that we analyzed in Sungai Pulai mangrove area, 6 of them are large with a total size of about 6,000 hectare. The interior of relatively large fragments tend to change less following fragmentation than it does at the forest margin. So this may be due to the age effects such as altered microclimate, which do not penetrate deep into the core habitat of the forest interior. So productivity is usually, according to some studies, productivity is usually stable in fragments of more than 9 hectares. So in that area that we analyzed, it is large of about 6,000. So therefore, it did not really change or reduce the productivity. So therefore, despite serious fragmentation, we notice an increase in this in GPP in this area. And another reason why GPP increase also could be due to the survival rate of trees or plants may be higher in relatively smaller patches because the abundance of solar radiation that is received along the edges may increase the productivity. Okay, so this is another study which we conducted very long time ago. I will just go quickly. So we published this work back in 2007. And during early 2000, the launching of high spatial resolution satellite sensors enabled the species classification of mangrove. So the first study was published in 2004, where the researchers use ICONOS data to classify 3 different mangrove species in the Caribbean coast of Panama. And in our study, we fused the panchromatic and multispectral ICONOS data and managed to classify 3 species. We used a linear mixture model. So this is a different showed previously. It is located here, very close to Singapore, and this area is called Tanjung Pelungko. And this is the spectral signature that we obtain from spectroradiometer, and this is as we get it from the satellite data. We can see the spectral signature of 4 features, including soil, are different, especially in the shortwave infrared region. And using this information and the linear mixture model, we could classify. So this is the spatial distribution of one of the mangrove species, which is Rhizophora apiculata. And I did not get the image of Rhizophora mucronata, but this is other groups which doesn't come under all the other species which do not come under Rhizophora apiculata and mucronata, we classified as others. And this is the fraction image of soil. So this is just to show that high spatial resolution images are capable of discriminating and classifying mangrove species, but they are not able to classify more classes due to the limited spectral bands that they have. And the last part that I would like to share a bit is about mangrove carbon. Mangroves are highly productive coastal habitat and most carbon dense ecosystem in the world, and they are known as blue carbon ecosystem. Studies have shown that they store 2 to 4 times more organic carbon per unit area than terrestrial forests. So growing mangrove can sequester carbon, and they can help to mitigate global warming or the impact of climate change. So mangroves have the highest climate change mitigation potential due to their carbon density and also of their scale of loss and restoration possibility. So therefore, lots of companies are now investing in growing mangroves so that they get carbon credits, which they can sell in the international market. This will be purchased by companies or governments that have committed themselves to net zero emission by certain target dates. In order to meet the target, these organizations, they do something by themselves to reduce their carbon footprint, or they can buy from the carbon market. So countries like Malaysia and India, I think they have big opportunity to earn money for climate action. For example, India, I just read this, announced programs for mangrove plantation in 2023 and 24 budget. And very recently, on December 1st, 2023, the World Bank announced ambitious plans for the growth of high integrity global carbon markets, with 15 countries set to earn income from the sale of carbon credits generated from preserving their forests, including mangroves. And Malaysia and India are not included in the 15 countries, but Vietnam and Indonesia, the largest country, is included. And so usually we use field-based in situ measurements or ground truth data to develop regression models for quantifying mangrove using remote sensing. So these may include biomass measurements like diameter at breast height and tree height, which are required for calculating mangrove above ground biomass, usually using allometric equations such as that of Komiyama, which can be used for the Asian or Southeast Asia. So again, this is an old study that we conducted back in 2010. Here we collected diameter at breast height of mangrove at 40 plots with 10 by 10 meter size, and we used Alos Palsa data with 12 by 12 meter resolution. So we used Komiyama's equation to get mangrove at the ground, and then we regress that using nonlinear equations with decibels that we extracted or received from Alos Palsa data. And then we scaled up to this region, and we get the highest mangrove of about 100 ton carbon per hectare, and the mean carbon is about 52 ton carbon per hectare. And this is another study in Malaysia conducted in another important mangrove area in the northern part of Peninsula. So here also Alos Palsa data was used. We use radar data because we want to overcome the cloud cover in optical data. So this study also used non-linear equations, and it was found that when the carbon content is more than 100 ton per hectare, then this kind of equation they do not really perform very well. And this is a very latest study conducted in Indonesia, where they used Sentinel-2 data, and they use the spectral bands as well as manipulation of the bands by calculating vegetation indices. And they used advanced machine learning techniques like extreme gradient boosting, and also genetic algorithms. So when they used this kind of advanced techniques, they could achieve a much higher accuracy of 0.8 compared to our previous studies in Malaysia. We only managed to get about less than 0.5 R squared values. And deep learnings can be used in this kind of works, but it should be remembered that deep learning needs a large amount of field data, and it is not easy to collect large data sets in mangrove, which is really very, mangrove is a very harsh environment, so it can be dangerous, it can be very time consuming, and also highly costly. And global canopy height data extracted from satellite-based LiDAR, such as the GLASS, geoscience laser altimeter system, I remember now. So it has been used together with the mangrove map produced by Chandragiri using Landsat to calculate biomass of mangroves worldwide. And also, as I said before, JEDI, the NASA's Global Ecosystem Dynamics Investigation, LIDAR, has also been used to get height estimates of mangrove forests. Okay, a few final slides. So remote sensing data can support policy actions, and they can inform policymakers about the trend in mangrove extent, changes in health, and identifying drivers of change, as I explained before. So with this, we can help to set targets for conservation and restoration. And through research, we contributed to Iskandar Malaysia Development Authority, who is looking after the development in Iskandar Malaysia region, and through low carbon blueprint. So we prepared a blueprint for them, policy actions for them to transform the region into a carbon low carbon region. So one of the action is action 10, which is green and blue infrastructure. So in this action, we proposed several programs to Iskandar Malaysia, and the latest information that I received from Iskandar Malaysia is out of 5 local authorities within the Iskandar Malaysia region, 2 authorities they have yet to do to implement these programs, but one of the local authority has completed all these actions, and one has completed 2 actions, and other authorities, they are implementing step by step. So my last slide, as for the conclusion, mangroves conservation efforts must be backed up by data, science-based evidence that the extent to which mangroves have changed. For example, any efforts involving large areas and need frequent updating can be supported by geospatial remote sensing data. Integration of socio-economic data can facilitate identification of drivers of mangrove deforestation or degradation. A hybrid method used by FAO combines the existing remote sensing mangrove maps for stratification and the participation of local interpreters for data collection and interpretation. In Indonesia, the mangrove assessment was developed as part of the FAO 2020 remote sensing survey. The aim of the assessment was to provide consistent indicators of mangrove extent, distribution, and trends to improve mangrove mapping in Indonesia for increased accuracy and efficiency. Local participants were used due to their local field knowledge of their studies, and so this is a network that we have in Malaysia called Malaysian Mangrove Research Alliance and Network. So we work together with other scientists who are interested in mangrove to produce more scientific data which can be channeled to authorities for conservation. So finally, I would like to acknowledge University Technology Malaysia and also the Ministry of Higher Education for providing funding to conduct these studies, and also Iskandar Development Regional Development Authorities for always supporting us, and postdoctoral candidates and PhD students. There are a few of them which I cannot name all of them here. So some of the activities that we involve in restoring mangroves. So we planted mangroves in a few places in Malaysia, and also we provide awareness program for companies and also for workers on the importance of mangroves and involve them in planting. So that is all from me. Thank you very much for listening, and I'm happy to take any questions. Thank you very much. Back to you, Dr. Nimit.
Thank you, Professor. This was actually very enlightening, and I'm sure that when our audience, when they see mangroves again, they won't be able to see like they have seen it before. So they will look at the mangroves, I'm sure that with new insights and all this information that they have, they would have in the back of their mind. They understand that how actually scientists monitor the mangroves and what are the importance of the mangroves, even if you are not a coastal community or you are not a fisherman yourself. We have some questions, and I'll just pass it on to you. So, first question goes in the way that the one of the audience they got interested in how can we determine the any canopy mapping with the use of the polarization that you said, VV, VH, HH, and HV. So probably that slide it created a spark, and maybe you want to just explain quickly, how actually scientists use that.
Yeah, so the polarization, usually SAR data has VV, HV, and HH polarizations. And VV polarizations are usually used for rough surfaces. So the signals are transmitted in vertical direction and also received in vertical direction. So when the surface is rough, let's say we have different types of mangrove with different canopy height, so that will help to get information from through this V and V polarization, and mostly from our experience, we found HV polarization can provide more information about mangrove because it is sent horizontally and it is received vertically. So therefore, when it is sent horizontally, it will especially we have to use L-band that can penetrate deeper into the canopy. It can also reach stems and branches and leaves. And when it comes vertically, which means it covers every part of the mangrove ecosystem. And it provides a brighter signal in the images, which help us to identify mangroves. If we use HV, for example, HV can provide information for smooth surfaces like water bodies. So if you want to detect water bodies, HH polarization will be helpful.
Right, that was rather very insightful. And one more question we'll take before we close. That question is more on the more like a community outreach. So what kind of because we have seen that there are economic interest and conflicts are there with the activities, and for coastal communities it is even if they understand how important mangroves are, especially after this 2004 tsunami, as we have seen, they will still have the conflicts in terms of their day-to-day economic activities and dependence. So how do you persuade them with the what kind of community outreach you persuade them, with the more towards the conservation part and creating alternate livelihoods that would be more on the sync of the conservation interests.
Yeah, thanks for the question, Dr. Nimit. Community outreach so far that we have conducted is not directly to the community who is living near the mangrove area, but usually companies, maybe this is a part of their social responsibility or CSR projects. uh, they would approach us to provide some sort of awareness to people of working in their companies. So we explain the importance, the significance of mangroves, as you said, how it helped during the 2004 Indian tsunamis and their carbon sequestration potential or pollution removal. So we provide this kind of information which is not known to them earlier. So with that, and we involve them directly in planting activities. So when they touch mangrove, when they get into the muddy environment, so they can feel it, they can understand how difficult it is, for the mangrove to survive. So we have to protect them. So this kind of outreach that we have done so far. But to be honest, my opinion is this kind of awareness program or restoration programs are piecemeal. They are not being conducted on a continuous manner. So when there is a need, then people go and plant, and it is just like a one-time activity. So there's no monitoring is going on to what happened to the mangroves that they planted. So what we have done in UTM is we have developed a mobile application which once we plant the trees, we will record their information, and after like about 3 months or so, and depending on the availability of funding, so we go back and look at the condition. But this is, to be honest, this is not happening so efficiently, but there is an opportunity. So this is what is happening at the moment. So I think a long-term monitoring activities need to be carried out by the local authorities or authorities responsible for mangrove conservation. And usually when we approach this sort of authorities, their main concern is funding. They say they don't have funding to do the monitoring. So there should be a way to do this.
That's very nice. That's very nice. And I think our countries have similar, social and socioeconomic experiences. So we can learn a lot from, each other's progress and processes. So
Definitely.
Thank you very much again. And I think this will be a very good time to, end this session, even though how interesting it is. I once again thank you very much for, taking your time out. I understand it is not just 1 hour, it's like also preparation and so on. But this was very insightful. And December being like, the month that we commemorate from 2004 tsunami in this region. So this was like really very like relevant one. Mangroves being considered as green walls. And yeah, thank you again. Thank you very much.
Thank you, Dr. Nimit, for the opportunity. And I think I enjoyed the talk. And thank you very much to the